All right, neural processing, the retina and beyond. Okay, so we've gotten to the primary visual cortex, or the striate cortex, our first level of higher level processing when we are in the cortical part of the brain, and not what I keep referring to as these subcortical structures. So I'm going to start with talking about the receptive fields, and I'm going to move on to talking about the organization or the mapping. This is already how we've done things, but one of the things I notice students get confused a lot are what's the difference between these receptive fields, so what the neurons are responding to, and the organization or mapping of these different areas. So we have these different feature detectors. Okay, we have simple cells, which tell us about orientation, complex cells, which tell us about orientation and direction of movement, and end-stopped cells or hypercomplex cells that tell us about length, angle, orientation, and direction of movement. We know about these from Hubel and Wiesel, again doing research on cats, and I'm going to share a video that I think is really fascinating that shows the measuring. So I'm going to show you the measuring of a receptive field of a simple cell in the visual cortex. But first I'm going to talk through the different cortical cells, and then so I can't actually give you this link until after I talk through these different cortical cells. So the simple cortical cell, first of all, if you notice on the left, we have this same kind of, there's excitatory, possibility of excitatory information and inhibitory information. And so I have a vertical bar. Okay, and if you can imagine looking straight forward, and there's a vertical bar hitting, let's say it's in the left visual field, it's hitting somewhere in the right visual cortex. So we have some cell in the right visual cortex that, if you notice at point 0, at this point of the cell, it's hitting vertically. That is where we see the most impulses per second. Once I get off of that vertical 0 point of any kind of oblique, if you kind of imagine how that starts to cross some of that inhibitory space, but if it's not too far oblique off of vertical, it's still hitting a lot of the excitatory space. I, as the simple cortical cell, I'm still going to respond, just not as strongly. And then as we move more and more oblique, where I'm hitting more and more of the inhibitory space and less of the excitatory space, I'm getting towards 0 to where when it gets to horizontal, I'm hitting inhibitory space as much as I am hitting excitatory space, if not more, and I'm at 0. Okay, so I'm basically just coding for, is this vertical, horizontal, or oblique? And if you remember from previous talks, we have more cells coding for vertical and horizontal than we do for oblique lines. If you remember, for the complex cell, it is responding to both orientation of line and direction of movement. So this actually comes with a story where Hubel and Wiesel, they spent some time in the visual cortex and they worked with those dots. You can kind of see on the screen there, there's dots, like they were working with in the optic nerve and what they saw in the lateral geniculate nucleus. And they were not getting any response from the neurons in the visual cortex. And they worked at this for a really long time. When you watch that video, I just want to bring up the fact that I usually show about 3 minutes of it in class. I've gone on and watched a little bit more, but I've never probably watched more than 5 or 6 minutes. These guys did this work for hours and hours a day, days of the week, weeks to months to years and years of their lives. And so here they were in the visual cortex working with these dots of light or darkness or whatever they were showing. And one day the cat was anesthetized and hooked up and everything. And they had the neuron hooked up while the slide was coming down. And as the slide came down, it got kind of stuck, and then they heard the neuron go off. I think it was David Hubel, who is quoted in their Nobel Prize winning speech as saying, the neuron went off like a machine gun. It was so exciting to them that this horizontal line that was moving down, that specific orientation in that specific direction was what had this neuron respond. And so they changed their stimuli, they got very excited, and that was the discovery of complex cells. Finally, I'm going to talk about the end-stop cells, sometimes called hypercomplex cells. Just to have you to show what's on this picture, though, you can see the complex cell on the left-hand side, that it is this oblique line when it's moving up and to the right, when that same oblique line is moving down and to the left. So you see the one with the asterisk, that same oblique line is moving down and to the left. There's no response. It's when it's moving up and to the right. And if we move off of the oblique, so as we move up from that in the picture, we're still hitting some of that, and we're doing something kind of similar. So there's some response in the cell, but really it's the asterisked one where that particular oblique line moving up and to the right, that's what that particular cell is responding to. That's the complex cell. The end-stop cells are, again, just a little bit more complex in that. So if we look at the example on the right, at the very top example, that they're trying to show that this is the part of the figure that is hitting the cell. Okay, so, and it's moving this time up and to the left, and if it's just that small portion and it's moving up and to the left, we see some neural firing. If it's moving down and to the right, nothing, right? It's really moving when it's moving up and to the left. And it has to do with orientation as well, but now we're going to see as we move that, so there's more of it, more of that crossing the kind of the receptive field where the asterisk is and the second one down. Now it's a little bit longer, has that same 90-degree angle, moving up and to the left. That's where we see the kind of peak of neural firing, where we see the most impulses per second, like we did in that first figure with the simple cell. Down and to the right, just nothing. We move it farther over that neuron's receptive field, and so it's even longer, and you can see that now we're slowing it down again. So really it's that particular length, that particular angle, moving up and to the left, up and to the left. And I think this is a good place to stop, and I'm going to strongly encourage you to go watch the link that I have, the link within the video, just for 2 or 3 minutes. You might want to watch it for 2 minutes or so and then move in, because it starts with the measuring of a simple cell. That's usually what I show in class, but if you move in a few minutes, they are measuring the receptive field of a complex cell as well. It's really kind of fascinating. And again, remember, these guys spent years of their life doing just this. And just so you know what's happening in that video, the sound is giving you the neural firing. I just wanted to have the summary slide, and I hope you paused or stopped and went and watched that video if it was possible for you there. If not, later, do that and have this summary of so far what we've seen of the neurons' receptive fields in the visual cortex. We have talked about the feature detectors. So simple cells coding for just orientation of line. Is it vertical, horizontal, or some level of oblique? Complex cells, which code for both the orientation of the line and the specific direction of movement. And end-stop cells that code for the orientation, the direction of movement, but also for the length and angle as well, as some of these have 90-degree angles or 45-degree angles. So as we've seen along the way, neurons are not just responding to light and not to absolute levels of light, but they respond to some patterns of light and not to others. As we move farther from the retina, those neurons are going to respond to more and more complex stimuli. We've already gone from center surround, just those little dots, to lines of different orientation, moving in different directions. But we want to put that together. Those are still features, right? And we want to put them together into us being able to see people's faces and the desks and the chairs and the couch and everything in the room. One of the things we're going to do before we move on from this kind of idea is to establish a link between the firing of those neurons and the experience of perception. And I think in this day and age, in the modern world, we think, of course, we see neural firing and that is being correlated with perception, and we all kind of know that, but we know that because of the research that has been done historically. So I'm going to go through a couple of different ways to answer this question of, do feature detectors, do those neurons and what they respond to actually affect perception? Okay, and the first kind of study is a selective adaptation experiment. And this is a psychophysical procedure where we're going to ask people, what is the smallest contrast that you can still see in these grading patterns? So when we talk about adaptation, what this means is that we have a decrease in response with prolonged exposure. We know that with neurons, the longer they are responding to something, they are fatiguing, and so their firing rate is going to gradually decrease, and we see a weakened response to a repeat of that same stimulus after they have adapted or fatigued. And we can use this information, we can use this kind of selective adaptation as a tool to study mechanisms of perception. So a selective adaptation study looks like this, and this is an example, right? We're going to do this with vertical lines, oblique lines, horizontal lines, all kinds of lines. I'm just going to give you an example of a vertical line. So we're going to present a vertical line. Neuron X, which is tuned to vertical lines, is going to fire. As we continue to make presentations of the vertical line in that particular part of the visual field, the neuron X is going to fire less often due to fatigue. Okay, we know this happens, and the question is, do these feature selective neurons affect perception? If so, then as I'm adapting that neuron to that feature, we should also selectively see a decrease of the ability to perceive that feature. The stimuli they use for examining this question are these grading patterns. And we can vary the contrast. So you can see in the left-hand image, the left circle has a high contrast. The black versus the gray are very different. And the right-hand circle has a lower contrast. And the question is, how low can I get that contrast before you really can't even see the horizontal lines at all? And you're basically guessing at what orientation you're seeing. We can also vary the orientation. So as I said, I gave the example of vertical lines, but we could use horizontal lines. We've used oblique lines so that we can look at this selective adaptation of these various orientations of line. And when we look at the grading patterns, a particular grading's contrast threshold is the difference in intensity at which the bars can just barely be seen. So we're looking for another kind of absolute threshold, but in this case, it's contrast. So if we go back to the left-hand image, we are lowering the contrast from the one on the left to the one on the right. And the circle on the right, if we kept lowering that contrast, again, there'd be a place where the bars could just barely be seen, and then you'd go into a place where you can't see them. And so we want to know, what is your contrast threshold? So the study looks something like what is on the left. If what I'm looking at is the question of these vertical bars and neurons that are responding to vertical lines, then what we do is we start by measuring the contrast threshold at a number of orientations. Okay, so vertical, various oblique lines, and horizontal lines. And then we're going to have somebody adapt to a high contrast grading. So they're going to look up at a fixation cross. We're going to have the grading, maybe they're looking right at it, maybe it's in a different part of the visual field, whatever, it's going to stay there. And as that person continues to look and look and look, the neurons that are responding to that grading are fatiguing, right? So they're adapting. And then after they've adapted, we go back and we remeasure all of those contrast thresholds to all of those orientations as we did above. And the expectation, right, is if feature detectors affect perception, then in this case, it should take a higher contrast for me to be able to see the vertical bars, because my neurons those neurons have fatigued to seeing the vertical bars. And the results are off to the right there in those figures, and you can see the adapting orientation, this kind of increase in contrast threshold. How much more contrast, how much more did we have to get towards black and white before the person was able to see the vertical bars versus these different orientations off of vertical. And if we treat vertical as 0, we get off to 20 degrees, off to 40 degrees. If we're really within 20 degrees, we see a drop off, but we still have to increase the threshold to some extent, because remember, if you go back to that slide that shows the simple cell responding to the vertical bar, that it is responding to those oblique lines that are not quite vertical. Actually, so that's what's shown in the right-hand side. I'm sitting here trying to imagine it because I was going to tell you this. Surprise! This is it looks exactly like, or very much like, the original simple cell response. So the simple cell is responding really strongly, many impulses per second to the vertical bar. That's the one that needs the highest increase in contrast threshold. It's still responding to those within about 20 degrees, and they need some increase in contrast threshold. And as we get out to about 40 degrees, where that vertical bar neuron was not responding really at all, then we don't need very much increase at all in contrast threshold, or really none. I usually feel like I've thrown people into deep water here with the selective adaptation studies, so think about if I need to explain some of that again, or if you have questions, let me know. Other evidence that we have for feature detectors affecting perception, well, one is the oblique effect itself, and that we see this entire pattern of results where, one, we have greater sensitivity to horizontal and vertical patterns. We can get that contrast threshold lower and lower for horizontal and vertical bars than for oblique bars. We have more neurons coding those orientations, and we see a greater fMRI response in the striate cortex to those orientations. So we are seeing the response of the feature detectors themselves, and that playing out in perceptual sensitivity. Finally, there's one more way I'm going to describe how they looked at this question of whether feature detectors were actually causing perception, so whether those neurons that were selective to certain features were affecting perception. And this was called a selective rearing kind of study. This is from Blakemore and Cooper, 1970. And they looked at kittens reared in a tube with a singular orientation. Okay, so in this example in the picture, the kitten is, while the visual system is developing, the kitten is only experiencing vertical lines. So if I remember correctly, the kittens spent their time in the dark, except for 5 hours a day they were in this vertical tube. And I don't love the kitten study, and nobody ever likes talking about it much. I remember one of the researchers somewhere says, you know, the kittens seemed happy when they were in the tube and all that, but it just is what it is. Okay, this is one of, back at this time we didn't have fMRIs or these kind of sophisticated ways of looking at brain activity. So this was how they examined this question. So they're really looking at the role of environment on the development of those feature detectors. So as the visual system is developing, and I'm going to go ahead and go to the results, because I leave the picture on there. What you can see to the right in the B part of the picture is that a horizontally reared cat. So the cats had these those cones on their heads, and they could be raised in a vertical world or horizontal world. And because of the cone, they really couldn't turn their head and get different kinds of views of these bars. So they're really mostly experiencing in this example, vertical, but maybe a teeny bit off as they move their head a little bit, teeny bit off. So the horizontally reared cat, when we look at the neurons, the neural response, we see neurons responding to horizontal bars, and then as they get to different levels of oblique, we see some response. But you can see in the first part of B there in that image that there just are no neurons at all responding to vertical bars or bars that are even really kind of slightly off, 10, 20 degrees off from vertical. And for the vertically reared cat, they have neurons that respond to vertical bars and some of the ones that are slightly off, oblique, but they have no neurons that are responding to those horizontal bars. They also wanted to see this difference in behavior, right? Because we want to know, does this affect perception? So the kittens, they would test them with this either a vertical or rod or horizontal rod, and the kittens would pay attention to, if they were reared in a vertical environment, they would pay attention to the vertical rod, but not to the horizontal rod. So they would swat at it and avoid it, but at the horizontal rod, they didn't even seem to see it. They would run right into it. They wouldn't swat at it or react to it in any way. So we see a difference in neural firing, and we see the corresponding difference in behavior.